Hello, I'm Spencer Ho at Salesforce. I'm part of the Activity Platform Clouds. So I'm going to tell the story about immutable big data. It is about the journey we had at the Activity Platform through the past few years. First, a little about myself. I started my career in networking, telecom, and the mobile device industry, moving through online game and online retail. Eventually, I landed in CRM SaaS. I like to work in the fields of data analytics, data engineering, stream processing, batch processing, and build applications on top of a database and storage. So if I have time, I enjoy watching TV and the movies, especially movies, but if I have time. I'm not a database expert. This is really a story about the application developer looking at the NoSQL databases and how to respond to them. So we'll go through the story now. Hopefully you'll enjoy them. So this is our agenda today. I will walk you through what is the definition of mutable big data, why and how we refactor, and what is the architecture principles for the refactors. And then I go a little bit on the implementation detail, especially the rule of thumbs. Then at the end, I'll widen up the scope, take a look at something that's in the work and also the new development in general in the industry. So this is really a case study following up another two blogs I have published at Salesforce. So this is based on the story and the development we have from an activity platform of Salesforce. So one of the activity platform's job is to collect emails, meetings, and other types of activity on behalf of Salesforce users. The collection pipeline is composed of a series of storm topologies. The story is really centered around a particular segment in the pipeline that is doing the store and indexing the activity records. So through all the years, we responded to those on-call issues, and we observed the nature of the traffic. We came to a conclusion on a certain design and the refactoring principles, and the principles really aligned with our day-to-day operations. So this is the part that a lot of software design is not, at least not emphasizing, how the design pattern should match with your day-to-day operations. And also, it's match to your use case and your technology at hand, their special characteristics. The activity records in our system is stored in the Cassandra tables. The Cassandra table is the system record. And each record has an indices in the, is indexed in the indices in the Elasticsearch cluster. Then this is the interesting part. What is the mutability? Why it is immutable? So if we look at the mutability, why this data is mutable? So there are actually two aspects. So the data itself mutates, the data change. It's just like a regular database record that has a modification, and it is changed to the data sets. But the other more interesting aspect is there are data coming into the data sets or be deleted from the data sets that cause the data sets to mutate. So let's take a look at what are the examples of those mutations. So for example, a meeting, when we ingest a meeting, the meeting actually is created right before or way before the meeting starts. So that means the meeting creation and ingestion is before meeting time. If you compare with the log, any log, the web log, the log is actually captured after the log is, the real event happen, right? So you have to click a link before the link click log get generated. So there's a causal relationship. But in the case of meeting, it's totally reverse. Right? The meeting has to be created first and captured into the system, but the meeting hasn't been held yet. So that changed how the data set being used and be ingested. We'll come to a more detail and explain why. There's another example, right? So if the activity data it be captured really long after the activity happened. For example, we just grant a license to a Salesforce user. So we actually ingest their activity data up to 6 months old. So that means at the present time, we get 6 months full of data. They have to be put into in their right position, right location, and that is an addition to the existing data sets. Right? So this is an addition which mutates the existing data set. So another example would be GDPR, the European GDPR. It requires the vendors to support data erasure on demand. Then that will be a subtraction or deletion from the existing data set. So the last example is the system generated data fields for some new features, new capability, especially nowadays with AI agents. There are a lot of data get augmented and annotated. And for some of the features, we can just enable them as it goes. But some of the feature we have to backport and regenerate data into the old data set, which is also addition to the existing data sets. So all this term I use, it is addition or detraction from existing data sets. But there's a requirement for us because most of the application we support is either UI interaction display or become a feature built for other for this to be the foundation of other features. And our requirement is something most of the time for the fetch filtering function to be completed in under 200 milliseconds. This pretty much rule out a data lake kind of a technology, like an iceberg, Apache Iceberg. So to iterate what I just mentioned, those examples. So it's really a two-time concept in those data sets. One is activity time, the other one is capture time. Right? For example, the meeting, Tuesday morning, 9 o'clock, that's a meeting time. If it's next Tuesday, not last Tuesday. And today, you're sitting there seeing this meeting records get captured into the system, but that is next week. So activity time is important to user, but to system, the capture time will greatly affect the database of storage, how it ingests, how it compact, how it index the data. Right. So activity time is not always earlier than capture time. The activity time can be, especially just in the case of a meeting, or in Salesforce case, there's a task. The task close date can be a month from today. And that makes the activity time is really later than the capture time. So that makes the off-shelf time series database is really not suitable for our use case. Why? The off-shelf time series database has this particular thing. It has a narrow window for data capture After that, it closed the data shards to optimize compaction, and it also optimized for file I/O. But in our system, the time the data get captured is more or less unpredictable. We cannot close the data shards. So that pretty much make those time series database or those storage engine not suitable for our use case. Not to mention those 200 milliseconds requirements. So now it comes to the refactoring, and we really refactor for operation. A lot of the design pattern talk about refactor for particular class hierarchy, particular concern. And our concern is one of the important concern here is how we operate. So before we go to the detail how this is operate, the pipeline segments in the story are two storm topologies. The first storm topology is the one right into Cassandra, and which is the system record, a NoSQL database. But Cassandra does not have the rich indexing capability. We paired Cassandra with Elasticsearch. So the second pipeline, which is again a storm topology, is to index the records into Elasticsearch. The first thing that we realize is this is really two separate databases. And we won't be able to, without any a significant cost, we don't do distributed transaction. There's no transaction semantics in here. And how do you guarantee the operation to an individual database will be really lockstep or even inconsistent? So we have to accept this is the eventual consistent. The two databases technically will never be in sync if there is a constant data traffic flow coming in. There's always a record just get put into Cassandra, but not yet in the Elasticsearch. Then this means it actually is a operational problem. First, how do you guarantee your data is not lost? There's no hiccup. There's no discrepancy. How do you guarantee the data referential integrity? So this is a quick overview of the processing graph. The cloud in the middle, that's within all this, this is a whole graph, especially for if you can see the two topology we're talking about. The persisting topology writing to Cassandra cluster, the indexing topology writing to Elasticsearch. And those error in between is all those pipelines talking to each other and with the direction, how they publish or ingest or processing. And those big error, those are the external, what we consider external data coming in, this entry point. So what I mean by refactor for operation. The first thing is, this is Silicon Valley. So we have to take care how much every team member understands every part of the system. You can see just how complicated this processing graph is. If there's any data discrepancy, we get a case, we get an alert, there's a backlog. Where is the problem? When you identify where the problem is, what is the root cause? This is something we struggle every single day. Right? If there's anything, we receive an investigation or we get an alert, how do we troubleshoot? So the first thing is time to diagnostics. Right? We have to take care. Not every team member on the team knows everything in the whole system. So the first thing is they have to be able to diagnose and also repair if the root cause is found, and really quickly And all those time for diagnostics and repair accounts for SLA. So if we can speed up the troubleshooting process, be able to identify where is the blockage in the pipeline, where is the problem in the processing graph, then simplify the pipeline will help you to not just identify and also find the root cause really fast. The second actually is a little bit not so obvious, because Cassandra and Elasticsearch is actually very, very different in terms of their internal build. I think that should be obvious to people. But in terms of API, it is not so obvious how those performance aspects, how those reliability, idempotent operation will be mapped to their API and how to optimize the operation. So once we separate the two, it is easier for us to optimize one pipeline, particular for one storage engine. So the first version of this whole pipeline, that was very early on, like at least 10 years ago. It is written in a way that's a service facade. It's a one or two function entry point and doing everything. It is very easy to prototype and show the capability of the system. But actually, it is really error prone because first, it is convoluted logic hide behind a few function entry point. If people is not familiar with the code, familiar with the processing logic, when there's a problem, for example, database down or a networking issue, there's a performance degradation, people won't be able to quickly identify where is the problem because the service facade is just encapsulate too much. All the intricacy behind the facade is lost on the new engineers. The second thing is, since the operation was hid behind the service facade, and how do you really measure, monitor, and later on optimize if the optimization has a conflict with the different parts of the code? Right? So this also affect the availability. So those are the challenges and also the things that we observe through operating those pipelines. So we come to some very, very simple architectural principle. So we want our processing pipeline be able to do at least once in order idempotent processing. This is really just this only one guideline for building the whole processing graph. So at least once give you delivery semantics. Say it will deliver. The second is it has to deliver in order. If this is run more than once, the processing result has to be idempotent. Right. We leverage a lot of retry logic, retry mechanism in the storm topology. Or to some extent, it's also all the streaming processing technology we have. And also, we rely on the database itself supporting the idempotent processing, idempotent writes. Think about, okay, I just talked about, we accept the fact the two databases are really two storage. And the traffic is constant coming in 24/7 into our system. Then there's no way to stop or verify between the two storages, whether when I have the record A in Cassandra and the record A is also in Elasticsearch. There's no way to do a really blanket-wide coverage for this verification. So we have to accept it, rely on a concept similar to eventual consistency, although eventual consistency in CAP is really referred to a homogeneous type of a server. It's not like a heterogeneous type of a system like Cassandra to Elasticsearch. But in our system, it is a sort of an eventual consistency. And the foundation of this eventual consistency is really at least once in order idempotent processing. So the implementation actually is, I like to go back and forth in the two slides. This is Cassandra and Elasticsearch. First, we come to Cassandra. Cassandra is really good in a way to do a really frequent, high volume individual writes. So each record, no matter it's a create, modify, or delete, you just do a multi-thread parallel, one record at a time, like a flooding to it. It can scale properly. You just scale your storm topology with your Cassandra cluster side by side. Pretty much we don't have any problem of a scaling up. But the trick is not just in Cassandra. Right? Elasticsearch actually is a totally different monster. So what we do is we write to Cassandra and make sure the write is complete, no error. We publish to Kafka topic, and the Elasticsearch indexing topology just picked up and start processing. So first, at least once in order idempotent processing is enforced in Cassandra. Then since it is in order idempotent at least once, so the message coming to the topic, to the Elasticsearch indexing topology will also be at least once in order idempotent processing. The idempotent processing part is in the Elasticsearch. But how do we do that? Because Elasticsearch actually is not good at a lot of individual, one document at a time indexing. That disrupt the cluster. Also, it make the throughput bad. Also, we have our special requirement because the at least once idempotent processing, that implies we may write or index a particular document more than once. That means we have to fix the document ID, and we have to enforce our own index sharding routing key. So that would pretty much take away anything that Elasticsearch recommends us for performance optimization. So the only thing that we can rely on is we do a batch write. So we implement micro batch indexing write in Elasticsearch, and we carefully cater to the error handling. Make sure it also has the idempotent at least once deliverable. Then after that, we were able to tune the throughput to Elasticsearch indexing on par with the Cassandra write. So there's no blockage through the pipeline. So in our system, actually, there are Spark streaming runtime and the Kafka streaming runtime. They are for different purpose. The Spark streaming doing something is really as a conduit, talking to other part of system outside the activity platform. And the Kafka streams taking care of a lot of AI model computation. So there are very different aspects. For example, Spark streaming, there are a lot of is a networking I/O bound issue, and Kafka streams have the memory and CPU bound computation, and we have a different way to optimize them. This is not covered in the story, but the spirit is pretty much the same. This is a big graph with the traffic constant flowing through it 24/7. It is very hard, or if it's not impossible, to build any validation mechanism. The only thing is the only thing we can count on is make sure it is at least once in order idempotent processing. So it will always deliver to the designated system for each processing function to do its job. Then we are sure the whole system is running as expected. And we talk about why we use Cassandra Elasticsearch, because that 200 millisecond constraint. Right? So can we use the data lake if it's something can give, for example, that time constraint, or we have a different time span for the data that when we pull out to support those application features. Something has to give in order to use a different technology. But once we change the storage engine, the processing pipeline has to respond accordingly. Think about if tomorrow we are going to write embeddings to vector database, what will we do? There's a lot of things that this processing pipeline has to adjust. On the top, it has to handle the traffic flow, the traffic pattern. And underneath, it has to respond to the storage engine it writes to. We come to this conclusion or have this principle is really based on the many years operation in this field. Then we get those, I would say this is some of the rule of thumb we bring to the team whenever we have a new engineers onboarding. This is Silicon Valley. We deal with attrition, deal with people rotation. That is a fact of life, and that will reflect into the software design and architecture design. So it's just putting this cliche, the total solution for a system. It's not just because a particular database you use that solve the problem. There's a lot of things in your processing pipeline can really help. When you're processing pipeline, you're processing logic, embrace the fact, the eventual consistency. A lot of the problem can be solved. I'll publish the original blog soon in medium.com. So you can find me over there. If you have any further questions, ping me on this email address. I'm on LinkedIn. Thank you very much. Thank you for listening to my story. Thank you.